Every year, more than 10 billion square meters of drywall are produced, enough to wrap around the earth, more than twice. It's cheap, it's white, it's everywhere. Yet behind this paper-faced panel lies a process powered by explosives, rotary kilns, and rollers the size of cars. How does crushed stone become the clean, flat wall you see every day? And how can we recycle it up to 10 times without losing strength? Before drywall can rise to frame our homes, it must be torn from the earth. And that journey begins in a place most of us will never see: an open-pit gypsum mine. In states like Iowa, Oklahoma, and Nevada, gypsum lies deep underground. Sedimentary mineral beds formed over 100 million years ago. To access it, surveyors map the terrain, identifying the richest seams, often containing over 80% pure calcium sulfate dihydrate. Precision drills bore down 30 meters or more, creating shafts for controlled explosions. Once the charges are packed and the signal goes out, a deep thud ripples through the mountain. Seconds later, thousands of tons of fractured gypsum collapse into dust-laced mounds. Here, excavators the size of two-story buildings swing into action, loading up to 40 tons per scoop into off-road haulers. These trucks aren't headed straight to the plant. Not yet. Instead, they rumble down gravel roads to a staging area where gypsum is sorted by purity and moisture. This step matters. The more impurities, like clay or quartz, in the load, the harder it is to produce strong, fair-rated panels later on. At this point, we're still just looking at rock. But within those off-white chunks lies the foundation for fire resistance, acoustic insulation, and rapid installation. And that's why it all starts here, deep beneath the surface, with a blast. Next, those rock piles are about to get crushed, filtered, and sent on a high-speed conveyor. Let's follow them inside the first stage of processing. At the processing plant, the silence of the mine gives way to the thunder of machinery. Freshly blasted gypsum rock arrives by the truckload, each carrying 30 to 40 tons, and is dumped into massive stockpiles. From here, front loaders scoop the stone into a feed hopper that leads to the primary crusher. This is no household grinder. These are jaw crushers that pulverize rock chunks down to 5 to 10 centimeters. But we're not done yet. To be usable, gypsum must become powder, fine enough to blend, mold, and set. So the next stop is a vertical roller mill, where massive steel rollers crush the gypsum to under 2 millimeters in size. The motion is relentless. Controlled pressure, applied evenly across rotating surfaces, turns rock into dust. But dust isn't just a byproduct, it's a hazard. Uncontrolled, gypsum dust can cause lung disease over time, including silicosis and lung cancer. That's why the entire line is shrouded in sealed ducts and vacuum extractors, pulling particulates away from workers. Meanwhile, a series of magnetic separators scan the crushed stream for stray metal, bolts, drill heads, anything that could damage the kiln downstream. From there, the fine gypsum flows onto a conveyor belt, just one of many. These belts stretch hundreds of meters, weaving through the plant like arteries, feeding each zone with a precise metered stream. This moment, between rock and powder, isn't just about size, it's about consistency. Every gram must behave the same in the kiln. Too wet and it won't calcine properly, too coarse and it'll weaken the panel. Next, we follow this powder into the heart of transformation, where flame meets chemistry and gypsum becomes stucco. Inside the calcination chamber, things heat up, literally. The fine gypsum powder, now carefully filtered and measured, enters a rotary kiln, a massive, slowly rotating cylinder lined with heat-resistant brick. At over 30 meters long, this kiln is the beating heart of the entire drywall process. Fired by natural gas or electric burners, the kiln creates internal temperatures ranging from 140 degrees to over 180 degrees. But it's not just about heat, it's about control. Sensors positioned along the kiln monitor thermal zones, adjusting fuel flow in real time to avoid sudden temperature spikes that could ruin the crystal structure. As the kiln turns, the powder is exposed gradually to rising heat. Here, calcium sulfate dihydrate, CaSO4 2H2O, loses its water molecules and transforms into calcium sulfate hemihydrate, CaSO4 0.5H2O, also known as stucco. Too fast and the gypsum burns. Too slow and the conversion stays incomplete. It's a delicate balance, choreographed by automation and fine-tuned by human oversight. Once calcined, the powder is air-cooled and sampled. In the on-site lab, technicians mix it with water in controlled proportions to measure setting time, expansion rate, and compressive strength, all under ASTM C472 standards. If the batch passes inspection, it moves to the mixing area. Here, the recipe comes together. 75 to 80% calcined gypsum, a water, and a small but critical blend of additives, like starch for bonding, K2SO4 to control set time, and sometimes glass fiber for added strength. The result is a creamy beige slurry, viscous yet spreadable, ready not just to pour, but to form the structural core of your living room wall. Next, this fluid mix will meet paper, precision rollers, and a race against time to become a finished sheet. The transformation from slurry to solid panel begins with paper, industrial kraft liner, often made from 100% recycled fibers, arriving in rolls up to 1,500 meters long. These rolls are fed into the production line with millimeter-level alignment, forming the foundation on which the gypsum core will bond. Unrolled and tensioned by a series of servo-driven rollers, the bottom paper layer glides forward smoothly. Above it, high-pressure nozzles spray a continuous layer of the freshly mixed gypsum slurry, creating a precise, even spread. Then comes the compression. A roller table presses gently across the top, smoothing the slurry while applying the top paper layer. Together, the sandwich of paper gypsum paper forms the classic drywall panel structure. But time is ticking. The entire mixture begins to set within 30 to 60 seconds, so thickness control has to happen instantly. Calibrated rollers adjust the profile to within plus 0.3 millimeters, depending on the product type. Standard 12.7 millimeter, 1/2 inch for walls, or 15.9 millimeters, 5/8 inch for fire-rated sheets. But air is the enemy. Tiny trapped bubbles can create weak points. So as the panel sets, an ultra-fine mist of deionized water and surfactant is sprayed from above, flattening the surface and helping voids collapse before they harden. Meanwhile, edge-shaping tools sculpt the side profiles, creating neat bevels for easier joint taping on-site. By the time the panel reaches the end of the forming line, it has gone from liquid to firm slab, ready to be cut. Sensors calculate length in real time, and synchronized industrial blades slice the ribbon into sheets. 2.4 meters, 3 meters, or any custom spec depending on market demand. And just like that, within less than 2 minutes, the panel has taken shape. But it's not yet ready to leave the factory floor. Before it can bear weight, it must face the drying oven. The cut panels now look like drywall, but they're still fragile, damp, and prone to cracking. To gain their final strength, they must enter the drying kiln, a massive, multi-zoned chamber stretching over 100 meters long, humming with hot air and sensors. Inside, temperatures range from 150 degrees to over 200 degrees, depending on the panel type and moisture level. Each drywall sheet spends around 30 to 40 minutes passing through the kiln on a moving belt. Hot air is recirculated and evenly distributed, drying each panel from the inside out to avoid surface hardening before the core is set. This is where drywall gets its resilience. Remove moisture too quickly, and the panel may crack. Too slowly, and the line backs up, wasting energy and space. After exiting the dryer, panels are inspected again, this time using AI-powered vision systems and infrared thermal cameras. They scan for warping, edge defects, or discoloration that might signal incomplete drying or material inconsistencies. Next, the panels roll into the edge sealing station. A layer of pre-printed paper tape is applied to both long sides, not just for aesthetics, but to protect against chipping and to display key certifications. ASTM C19396 compliance, fire resistance ratings, and brand logos. and sometimes QR codes for digital traceability. From here, forklifts stack the panels into 2-ton blocks, about 80 sheets per pallet. They're arranged with precision to reduce breakage and shrink-wrapped for transport. In the warehouse, a computer-managed system assigns every batch a code for inventory tracking, quality assurance, and just-in-time logistics. Within hours, these drywall stacks are loaded onto trucks, ready to ship out to job sites and distributors across the country. But what if we could avoid shipping altogether? By recycling drywall right at the source. That's exactly what's happening across the Atlantic. Across the Atlantic, a quiet revolution is reshaping the way drywall lives and relives its purpose. In Europe, demolition doesn't mean the end. Old drywall panels are systematically collected, sorted, and transported to dedicated recycling centers. In countries like Denmark, the Netherlands, and Germany, over 50% of gypsum waste is now recovered, processed, and reborn. It starts with mechanical separation. Recycled panels are crushed, stripped of paper facing, and ground into a fine powder. The core gypsum is screened for contaminants and rehydrated into a fresh slurry, ready to be used again. Unlike many building materials, gypsum doesn't degrade much when reprocessed. It can be recycled up to 10 times, still meeting strength and fire resistance requirements. But Europe goes further. Some facilities also recycle the paper facing, which is collected from household and industrial waste, cleaned, pulped, and reintroduced into the board. This not only strengthens the final product, but reduces reliance on virgin trees and imported pulp. The economic advantage is clear. While recycled gypsum costs 60–70% less than newly mined material, emissions drop dramatically since quarrying, blasting, and hauling are avoided. A less landfill, more loop. Meanwhile, in the US, drywall recycling is still emerging. Most states lack infrastructure or mandates to separate gypsum waste. But that's changing. California, New Jersey, and Washington are piloting closed-loop recycling systems for construction debris. Landfill bans on gypsum, combined with rising landfill fees, are pushing developers to rethink waste. And with more than 75 million tons of drywall expected to be discarded in the US over the next 2 decades, the stakes couldn't be higher. Drywall isn't just a building product. It's becoming a circular material, ready for a second life and a third. Look around you. That flat, white surface behind your bookshelf, the one you've painted, drilled into, maybe even patched, started life as rock, was fired in a kiln, rolled at speed, and trimmed by machines running 24/7. It traveled hundreds of miles, passed dozens of quality checks, and may one day be ground down, rehydrated, and reborn again. Drywall may seem invisible, but behind it lies one of the most optimized, energy-aware industrial chains in modern construction. It represents the shift from raw extraction to precision chemistry, from single-use to circular life cycle. A humble panel that quietly connects homes, schools, hospitals, and offices, while increasingly asking less of the planet. And that's the wonder of materials engineering. When done right, the ordinary becomes essential. The disposable becomes durable. The wall becomes the story. So the next time you walk into a room and tap the wall, remember, there's more behind it than studs and screws. If this journey gave you a new perspective on the materials around you, leave a comment below. What other factory stories do you want us to explore next? And if you haven't already, subscribe and let's keep discovering how the world is made.